Here is the definition of linearly dependent elements or vectors or members. Let K be an extension of the field F, then the vectors K1, K2, K3 vectors भन्दा नि elements भनौं यसमा, then the elements of K are said to be linearly dependent if this sum is equal to 0 for some AMs from the field F, at least one of Ki's is equal to 0. Means if this sum is equal to 0, then either A1 is 0 or B1 is 0, A2 is 0, A3, A4, AM, any one of them, at least any one of them is 0. I'm telling about A, not K, okay? Okay, means at least any one of them should be 0. Then we say that these vectors K1, K2, Kn, Km are linearly dependent. And what is the definition of linearly independent vector? Let K be an K be a field extension of a field F, then the set of elements K1, K2 up to Km are said to be linearly independent if A1, K1, A2, K2 plus dot 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 up to An, Kn is equal to 0 for AI is the element of F, then A1 is equal to 0, A2 is equal to 0. It means every value every value A1, A2, A3 from F, they all should be equal to 0. This is the difference between the definition of linearly dependent element and linearly independent elements. In dependent elements, at least one of AI's should be 0, but in linearly independent elements, every element should be equal to 0. अलिकति अझै यसलाई मिलाउँछु है, अलिकति यहाँ भनाइ मिलेन. Then at least one of is not equal to 0 भनेको कम से कम एउटा 0 अथवा यसलाई अर्को भाषामा यसरी लेखौँ, अझै यो भाषा मिलिरहेको छैन. For AM is 0, then at least नभनौँ sum of AI's are not equal to 0. Means सबै यो 0 हुन्छ भन्ने छैन. जब कि यसमा के हुन्छ भने हरेक एलिमेन्ट 0 हुनुपर्छ. This is the difference of definition of linearly dependent and linearly independent elements. Now, basis भन्ने एउटा word आउँछ. What is a basis? Let K be a field extension of F, then the set of elements E1, E2 up to EM are said to be basis elements of K are said to be basis elements of K if E1, E1, E2, E2, if E1, E2 dot EM are linearly independent. If they are linearly independent, means they follow this criteria and they can generate field. They can generate field K, means any element of field K can be written as the linear combination of these elements. Then we say this set of vectors, this set of elements are known as basis of the field K. So यो भनेको के generates के भनेको के हो भने is that for every any element you take from K, suppose that is a element what you will take H, suppose that H is the element of K, then there exists some scalars in field F such that H can be written as the linear combination of B1 E1, B2 E2 and BM EM. So I have shown you here that the element H is generated by the basis elements and they are linearly independent also. Then we say that this set of elements, EM elements, are basis of the field K. Okay, this is now our theorem. Transitivity of finite extension. The statement of the theorem is if L is the finite extension of K, L is extended finitely up to K, okay, and K is a finite extension of F, means K is extended finitely by F, then I have to show that L will be a finite extension of F. First thing, L is a finite extension of F, we have to prove, and furthermore I have to show here the number of basis element in LF is equal to the number of basis element in LK multiplied by number of basis element in KF. So this represents the LK represents or LF represents the number of basis elements in this extension, okay, that is called degree of finite extension. So I will show you this. Since L is finite, uh, since L is a superfield of K and K is a superfield of F, so obviously we can write that F is a subset of K and K is a subset of L. This is very obvious. Let the number of basis element in Kf is given by n, and number of basis element or degree of finite field extension of Lf or Lk is given by m. Suppose that the finite extension of K, L in K is m and K in F is n. Means this represents the number of basis elements they contain. Okay, let E1, E2 dot up to En be basis elements of this Kf and another F1, F2 up to FMB basis elements of Lk. This means any element of Kf can be generated by these vectors, these elements, or any element of Lk means L can be generated by this set of basis vectors, basis elements. Okay, so now we will claim, we will mix up them. We claim that a set of elements EIFJ. How many elements are there? There are many elements like E1F1, E1F2, E1F3 up to E1FM, and then E2F1, E2F2, E2F3, and so on, so on. This will go finitely up to ENFM, the final basis element. This element where I is limited from 1 to n and j is limited from 1 to m. This is its limitation. This set of elements, we claim that this set of elements is the basis element of finite extension of L over F. For this, to show this, I will take any element from L. Let alpha be any element of L. So alpha can be expressed actually when alpha is the element of L. Look at here, this, and Lk has m basis elements. So this alpha can be shown as a linear combination of these vectors. So alpha can be written as B1 F1, B2 F2 up to BMFM. This element can be expressed as the linear combination of these vectors, which is are from, I have taken it from Lk, therefore they are the elements of K. Okay, in short, you can write down this sigma of j moves from 1 to m. This is B, J, and F, J. In short, you can write down this. Now again, you see here that Bj is the element of K. So Bj also can, Bj is the element of K, and look at here, Kf has n basis elements of this. So Bj can be written as the linear combination of these vectors. Again, Bj, taking j as a fixed term, I can write it that alpha 1j E1 alpha, 2j E2, and so on. Finally, sorry, I'm telling it is lambda, lambda 1j E1, lambda 2j E2, and so on. Finally, to final value lambda nj E n. Up to here we will write down. In short, for lambda ij is taken, this value is taken from this k of, therefore these constant terms or these numbers are taken from f. In short, you can write down bj is equal to sigma I is equal to 1 to n lambda of ij and e I. In short, you will write down this. I will put the value of bj from here to here. I will put the value of this bj. Okay, I will mix up these two results. From 1 and 2, I can write down that alpha is equal to sigma of j from 1 to n, and inside the bracket I is from 1 to n lambda ij ei and fj. I have substituted the value of bj over here. This is the value of bj. Therefore, alpha can be written as in a single summation I and j. Here I moves from 1 to n and j moves from 1 to m. This can be written as lambda ij e I and of j. For lambda ij is from f. This particular number is from f. So I look here that alpha can be shown as the linear combination of these vectors. Since alpha is shown as the linear combination of these vectors, so these vectors can generate. This implies the set of vectors ei fj can generate to the field L. And now we have to show that these vectors are linearly independent. To show EIFJ the language program to show the elements in the set of these generator elements to show the elements in the set of these elements are linearly independent. Independent generator दुईटै देखाउनु पर्छ बेसिस हुनको लागि. So I will show it is linearly independent. Okay, let us take some constant term multiplying mu ij e j f I e I f j that is equal to 0. In the case this summation is 0. Okay, it means there are many numbers of terms in this summation that is 0. Okay, it is obvious that I moves from 1 to n and j moves from 1 to m as done before, that I is running from 1 to n and j is running from 1 to m. If this is equal to 0, then I have to show you that individually this mij every value will be 0. Okay, so I will, this will imply you that sigma j, I have separated this value, sigma mu ji ij and ei, I have taken fj outside, that is equal to 0. In this case, fi is the basis vector. Since fj means taken from this value, these are the basis vectors. Basis means they are linearly independent. Since the set of fj are linearly independent, so this multiplying factor, this constant will always be 0. This shows you that sigma mu ij ei is equal to 0 for every value is 0. So this sum is also 0. And since ei is also the basis vector of, you can see here that ei's are the basis vector of k in f. Since these are the basis vector, therefore they will be linearly independent, therefore this constant term will be equal to 0. Since the set ei is basis of or linearly independent are linearly independent, so the constant term which is multiplying to ei, they all will be individually, they will be equal to 0. Therefore mu ij will be equal to 0 for every I and j. So I have shown here that we have started from here, that in the case this value is equal to 0, then every mu ij is 0. This shows that this set of EIFJ vector are linearly independent. So this implies that EIFJ contains linearly independent elements. So I have proved here that they are linearly independent. Since they are also generators, since they are also generators, they are also generators of L. So EIFJ forms a basis of L over F. Okay, this way we have shown here. And you can tell me how many basis elements are here. So here are m into n basis elements. So we can further conclude that how many basis elements are here? It is m into n. So L, the basis number of basis element in LF is exactly equal to m into n. That will be L k into k f. So finally I have proved here that LF is equal to LK into KF. This way we have completed our theorem